Yeah, so from today, I give up to give the lecture for the like the people who are not like the worthy for the lectures. So, but it's just a free conversation. It doesn't mean that we should restrict our conversation to the notes that I already post. But after our conversation, I can provide further notes to make some further clarification. One thing I post for this week. It does not mean that I want to just focus on the conversation on my notes, but still, because I make at least summarizing what I did like to tell last week. So the current concept of chern connection, let me just mention briefly. Why at least complex geometry like the community must care such a like the concept. In order to talk about the concept of the connection, connection is defined over the vector bundle. Vector bundle. So the vector bundle is this E stands for the vector, but this is also one of the another smooth manifold that has a so-called submersion, Riemannian submersion, and we are so-called the local trivialization, so that we can identify locally this E as an open subset times R to the K is the rank of the fiber. So that's the basic assumption on the vector bundle, and we don't assume yet M should be the complex manifold. And the sections of the given vector bundle can be visualized in this way, so that if we just compose this like the projection map pi, then we just recover the identity on the complex on the given smooth manifold. And we can also look at the local sections, meaning that so we just choose the open subset and just repeat the definition. When we look at the smooth sections, that means that we choose the gradient structure. So with each like the k, this just means that this omega stands for the differential form, and we take the tensor product to k make the k like the vector fields for the free slot. For each k we allow to plug in the vector fields k times. So that's the meaning. And we also know from linear algebra that if we assume, let's just assume from now on that this is now the complex vector bundle over the complex manifold, basically, because that's our main consideration. And if we already have the Hermitian metric defined fiber wisely on complex vector bundle E, then if we change the basis via the coordinate change like the matrix, then we know that corresponding matrix representation of the inner product fiber wisely should be written in terms of in terms of the conjugation. So we are know from linear algebra, I assume this is kind of okay. And if the rank of the fiber equals one, in such a case, such a complex vector bundle is called a line bundle. Line bundle, then this just effect fiber wisely is just nothing but the scalar, so that we just have the merging them together to get the norm square of some function. So that there's a just transition function, so that we know how can we change from one coordinate to another coordinate in terms of the transition function. That means that the real the geometric data of this each line bundle. So all we need to describe is the open subset from the given smooth manifold M with the transition function. So our necessary data for the complex line bundle should be those just a pair, this pair. But if it require holomorphic line bundle, then we just require transition function. By its consideration, it must be non-vanishing for sure, but we also require this should be the holomorphic like the function. So this O star just represent the non-vanishing holomorphic function. So the classification of the complex manifold are usually given in terms of the canonical line bundle. So we just mentioned this last time briefly, that what we do is we start from the arbitrarily complex manifold, and we have a holomorphic cotangent bundle, and we assume this is dimension n, so that we take the n times wedge product. So after taking the n times wedge product, then you can just assume that the the local section look like something like this. So via the choice of the some local coordinate, then this DZ1 wedge to the DZN wedge. So this must be rank 1, so that the effect of the fiber should be written here as f. And for a moment, this f is just a smooth function. That does not need to be the holomorphic in general. So, and what we know is we change the open subset for the n differential forms, then there should be the effect of the determinant. That's what we know from the the differential forms. So that this must be the effect of the transition for sure. So if we just really look at this description here. So if you just compare the description of the transition here from the one expression of the differential form n form to the another differential n form, then there's an effect of the changing the coordinate. Whereas if we already have the Hermitian metric on the line bundle, then we must have the norm square of the transition function. So this effect should be related to this guy, so that we can try to match this expression via this concrete expression of the canonical line bundle. Then what should be the Hermitian metric defined on the canonical line bundle? Then what we know is the following. So let's just assume the base complex manifold is equipped with the Kähler metric for the simplicity. So in such a case, we know that then if we already describe the Kähler metric, which is Hermitian metric, in some open subset in local coordinate, then via the another coordinate, then this is the effect of the change the coordinate in a way that you can now see the effect of the indices ij should be here. But if you want to change the coordinate from KL to ij, then this like the tensor indices k and k sum together, and L also sum together, and there's an effect of ij here. So that this is the way to change the coordinate from G sub KL to G sub ij bar in this like the change of the coordinate basically. Then if you just put the determinant of the each expressions of the here and here with the different coordinate with the overlap, then we should get the product, the square of the coordinate change, like the effect, so that we get exactly this expression. So this is this f sub beta alpha just represent this guy. And if you take the determinant in this level, then this expression should appear twice. So that's why this becomes norm squared to the -2. So this -2 is just from the interpretation of this expression. So if we just rewrite this expression with just flipping the numerator with denominator, then we basically get this. So this explains that this expression must be the Hermitian metric on the canonical line bundle, because this exactly match with the desired expression over here, so that we get this guy. So we can simply just summarize the following. So if we have the complex manifold, we don't even assume this to be compact. So complex manifold equipped with the Kähler metric G, then we can consider the 1 over determinant of G, which is positive for sure for each point of the manifold. Then we can just choose this as a Hermitian metric on the canonical line bundle. Then, so what we'd like to say is let's just skip everything for a moment. And this is just the example in the case of the complex projective space. So what we want to do is the following. So let me just reshare the previous note of the last week, I think. So this is the previous note. What can we do? So if you look at this expression of the Lich curvature, so this identity is the identity in Riemannian geometry in the case of the Kähler. So Lich tensor, Lich like the two form is written as a negative partial d bar of log of the determinant of G. And you also know, on the other hand, what we saw in the case of the canonical line bundle, that the Hermitian metric on the canonical line bundle is written as 1 over determinant of G, as you can check from here. If you compare, if you put this negative sign inside, because there's a log here, so this becomes just a 1 over determinant. 1 over determinant, what can you see? So dd bar of the log of the Hermitian metric becomes the Lich curvature. So that this is the way to connect the information of the line bundle with the word of the Riemannian geometry in a way that usually if we start from the line bundle, general line bundle, then line bundle is equipped with the Hermitian metric. Hermitian metric. Then if you just mimic this expression of the dd bar of log of the Hermitian, like the metric with the just non-vanishing, like the sections, local sections, then we get the curvature to form. And in the case of the line, canonical line bundle, that becomes exactly the least curvature of the Kähler metric from the base Kähler manifold. So that so this is the way to, depending on the sign of the least curvature, we can just associate the information of the line bundle, canonical line bundle. Then we can kind of forget about the differential geometric data, and we can use this like the link to classify the complex manifold. So usually the classification of complex manifold is given in the following way. So start from the complex manifold, then without a consideration of the Kähler metric, still we can talk about the Hermitian metric in general. We can still talk about the Hermitian metric. Then we can talk about the curvature to form. Then via the sign of the curvature to form, we can give the description of the classification of the complex manifold. So that's the way to just do in this way. So as I said already over here. So even I said the classes of the Fano, Calabi, and general type are given in terms of the sign of the Lich curvature in Riemannian geometry, but that's not required. So if we already equip with the Kähler metric, we can simply just do this for sure. But in fact, all necessary data we need is just a data of the canonical line bundle, and based on it, we can kind of forget about the metric because we know we can generalize these expressions in terms of the data of the canonical line bundle. So that's a very vague idea. Is that okay with you? What I'm talking about? So let me know if you have any like comments or questions. I just mentioned everything very vaguely. Yeah, Alan,
So,
cool.
so the idea is like basically uh, in last class we saw that like Vicky curvature like in terms of the like uh, Riemannian metric.
Right.
Now, instead of going to the Riemannian metric, it's just enough to look at the Hermitian metric on the line bundle.
Yep.
That's the idea that you are selling, right?
Yep.
Okay.
So let
Uh,
me be more precise. Why we can really
mm,
say we can forget about the Riemannian metric in the context of the especially the Calabi conjecture. Now let me share my like the iPad. So why I can simply say we can indeed forget about the effect of the metric. So this is the rest of the note. I'd like to just provide the not just the explanation of the mathematical detail, but the like the structure, topological structure. So what we can really expect. So if you have the complex manifold, and this L is taken as a canonical line bundle, So for example, so even let me just choose G1 and G2 for just simplicity. So let's just assume we have a two Kähler matrix. Doesn't need to be Kähler metric for this description, but this gives some
mm,
basic
mm,
idea. So that
mm,
now if we just provide two Kähler metrics, then what we can do is one is negative dd bar of log of determinant of G1 for sure. Another one is, let me call this by curvature to form, so that this is, let me call it by Lich of the G1. And also we have another one, negative dd bar of log of determinant of G2. This is Lich of G2 for sure. Yeah, so up to everything is clear from the structure. And what we know for the partial D and partial D bar is exterior derivative should be decomposed in this way.
yes.
And we also know that the square equals 0 always for the exterior
Mm,
derivative. So if we just rewrite this as a partial d plus partial d bar square, this is equivalent to say
correct.
for sure. So
Mm,
then if you look at this description here, this is already written as a partial d bar, so that if
yes.
we put exterior derivative on this expression, whatever this is, so this
Mm,
must be 0. no matter what.
Mm.
So this is already guaranteed. So this means the following. So this means if you look at this guy, then we can just say this is equal to 0. This is equal to 0. Is that okay with you? This is guaranteed. And on the other hand, this guy is real differential two form. And in fact, this is so-called differential one-on form.
Mm.
But basically just that this is a differential, real differential two form. That means what? We can talk about the equivalent class. We can talk about the equivalent class in the second drum cohomology. In fact, this is actually Z for the compact scalar, but let me say C. So this is indeed the definition of so-called the first chunk class. And as the notation represent, this actually does not depend on G1. So indeed, so if you look at this guy, then by the description of the negative dd bar of log, so that you can easily see that this should be equals negative dd bar of log. Now there's the place of the log here, determinant of G1 over determinant of G2.
Mm.
Is that okay with you? So here's a magic. Why this expression matters. The magic is that when we describe the determinant, so of the so-called Gij bar in this level, then this indices depends on the local coordinate for sure. So the basic line is that we start from the manifold, then we choose the coordinate, local coordinate, then we describe Gij bar because this Gij bar is indeed coming from ddzi with ddzi like this. So that if we try to expand this open subset, we cannot in general expand to the global complex matter. That's not guaranteed other than the Cn. However, so because we choose the different Kähler metric, so the effect of the changing the matrix will cancel together. So the part is this is defined globally.
Yes.
So each of the numerator and denominator are defined only locally for sure. However, it cancels the effect of changing the coordinate. So
Mm.
therefore, the ratio itself is the smooth function defined on the entire complex manifold. That
Mm.
means that if you look at the representative in drum cohomology as a drum cohomology class, they must be the same. Because
Mm.
this just means that if you have a one differential form, another differential form, so if we take the subtraction, this should be written as a d of the eta, basically. And this eta should be so globally defined like the object. I'm saying very like the roughly. And because of this description, whatever metrics we choose, the representative in drum cohomology class are always the same. So that it makes sense to just say this concept of the representative does not depend on the metric. So that's why we call this by the first chunk class. First chunk class. Does that make sense to you? So that's why this expression is so important. And the rest of the the note, now let me just go back to my note. All right. So what we got, where were we? What we got is the following. So the rest of the details give you that if
Okay.
you have,
Yes.
yep, sure, please.
20%. So, you just got to see that Ricky curvature of G1 minus Ricky curvature of G2, the two form, the difference between them is globally different. How does it ensure that it belongs to zero in the second rank homology class? In the sense, that's why we are able to tell that the equivalence class, it becomes just go to the place wherever you are writing.
As I said, so let me just reshare. Add. So yeah. As I said, the basic line is if you have just a say Riemannian manifold, then we choose a local coordinate. So say
Just to notify that I understand that it is globally different because the both change of basis matrix will get cancelled in the numerator and denominator. They'll appear in the numerator and
yep,
denominator. They'll cancel each other. That's
yep.
perfect. My question is, you have written in the first page that implies Ricky curvature of G1 equivalence class is equal to Ricky curvature of G2. In the second, you have Ramakrishna class. How are we able to tell that basically that will happen if the difference between them in the previous page, the difference expression should be in the zeros. So how
I
do we
under
tell
yeah,
that some element?
yeah, I understand your question. So in fact, this is actually quite really deep. Let me explain this way. Mm, so few things. Instead of just writing the note, let me just share the fundamental lemma in complex geometry that we actually rely on this indeed a lot. And I think in this way, I can explain the spirit of the Calabi conjecture as well. So yeah, so this is also one of the recommended like a reference to study complex geometry for the people who didn't study complex geometry yet. So one of the important like the lemma is so-called the Didi-Bar lemma. Didi-Bar lemma gives you the answer. Yeah, this guy. So you are asking this. You are asking this. So if you look at this
Um,
statement here, by
mm,
the way, compactness matters. So in the case of the bounded domain in Cn and the
mm,
non-compact Kähler manifold, we basically lose Didi-Bar lemma. And for the
mm,
non-Kähler world also, it basically lose the Didi-Bar lemma so that it makes the all technicality details very difficult. And the Didi-Bar lemma is a consequence from the Hodge theorem. So I will not talk about the proof, but if any of you are interested in like proof, I'm very happy to provide in as consuming for one week. This is very worthwhile to do so. But if you now look at this description, this already gives you the answer of your like the comment. This is
mm, mm,
very like the deep like the result. So omega and eta, let's just assume they are all real one-on form. And the examples are rich one-on forms are such a, like the examples. And what we assume is if we have so they already share the same cohomology class. That's the assumption. That's the assumption here. Then what we can do is that so this means what? So the omega and the eta, if you take the subtraction, it should be written as a so because this is differential two form, so that we are able to find the differential one form, that d of the differential one form should be the difference of those two. That's the meaning. But instead of using the exterior derivative, we are able to find the real value of someone's function so that d of the differential one form can be denoted can be represented by I times partial d bar times f. So in fact, they are equivalent. So rather than saying the exterior derivative with the one form, we are in fact able to write in this way and vice versa. So this gives you the answer, right?
just so is compactness is a necessary condition?
Compactness is necessary condition. So for the non-compact cases, so we only look at the setting that we can do this. It's not in
Mm,
general
mm,
guarantee. So like the
yes,
description of the Bergman metric written as a DD bar of the log of the Bergman corner, those are by
mm,
the definition, we start from there that we can just represent in a nice way. But in general,
um,
so this is not guaranteed for the non-compact like
uh,
the setting.
mm, mm, um, yeah,
Yeah, this is for
and
like the detail. Mhm.
yeah, yeah, got it.
Okay, so then I think now we can understand
Yeah,
the
I have
yeah.
a one question.
Sure, go ahead, Parvati.
Yeah, so I'm not getting where we use the determinant bundle of cotangent space
Okay, let's just
for defining Hermitian metric. So what happens if you choose a arbitrary line bundle? Is it possible to construct a Hermitian metric for arbitrary line bundle instead of the canonical bundle?
So I understand your point. Let me just think about this.
Yeah, here I'm not getting the importance of the canonical line bundle to define a Hermitian metric.
Yeah. So yeah, I love all those like the comments and questions. And yeah, I think yeah, we are in the like a good mood to now learn something together. So there are the Berard's question, in my understanding, would be the following. So if we start from the compact Kähler manifold, so that it is already equipped with the Kähler metric, then we can choose one of the line, just a Hermitian metric on the canonical line bundle as a 1 over determinant of G, because G was already declared. In that case, we can associate to the Leech curvature as a one of the real one-on form so that we can do something. But in general, so if we start from the arbitrary complex manifold, and then if we just put arbitrary holomorphic line bundle, then, so among them, why? So first question, why canonical line bundle is important? Two, can we find the line, like the Hermitian metric on the general line bundle? So that kind of the questions should be appear.
Yes,
So
yes, yes, exactly. Yeah.
so the importance is one of the fields matter like the result. So let me just show you that result. So let me split into two pieces. So by just following the details in this note that I provide, what is the definition of the chern connection, and from the description of the chern connection, and by saying blah blah blah, and then we are able to describe the first chunk class in a way of minus d bar log of determinant of Hermitian line, like a Hermitian metric. So this description is I already explained, and the detail is already written here. So let's just assume we already know the churn connection and we know how to drive this. So let's just assume that. So if I just go back to here, so we now start from the complex vector bundle, and let's just assume we have at least one Hermitian metric. So this is not the construction, but we just assume if we already have the Hermitian metric. Is that okay with you? We already have the Hermitian metric. So in such a case, this is just a consideration of the churn connection. Let me just show you the form of the curvature. So the curvature of the churn connection, this lemma is exactly what I drive in my note. So let's just assume we already know this. So, and in order to get this expression, what we do is, so because this is a Hermitian metric, define fiber wisely, we just put local holomorphic section inside so that this is positive. This is just a local section. And then, and this is a first chunk class. So the statement, what we'd like to say would be the following. So this is a Field's-Mendel result called the Godaira embedding theorem. So let's just look at now this guy. Now look at this guy. So two things. So number one, the first chunk class being positive condition, it does not require the Hermitian metric at all. Let me just repeat. I'm not saying that we are caring whether or not we can construct the interesting Hermitian metric. What I'm saying is that the statement of first chunklets being positive is independent to the existence of the Hermitian metric first. Let me just explain algebraically. So this condition means the following. So if you start from the complex manifold, now I don't care the metric at all. I don't care. So all I care is then, so if you have like a complex manifold, then if you guys are interested, I can talk about some basic language of the complex algebraic geometry as well. So there are the notion of the so-called shapes. Let me just do not explain the concept of shapes today, because depending on your interest, we can go this direction also as well. Then there are three important like the shapes. One is the constant shapes given by the z. Another shape is the shape of the holomorphic functions. So this just means that if you plug in open subsets, then this will give you that holomorphic functions define on O, define on U. That's the meaning. And there's a O star that we already used. So this is a non-vanishing. So shift of non-vanishing Holonomic functions. So the reason why I mentioned this R plus sudden, then this is extremely important, like the example that we can always induce the short exact sequence for arbitrarily complex manifold. It does not require any condition. That so there's a exactness from Z to O star. And this is just a injective. So this is just a constant like the shift, so that it just a constant will be just a map to the holomorphic function as a constant function. And this guy is the exponential of the 2 pi I of the function here. So if you choose one function here, then we can always just make to be this guy to the non-vanishing holomorphic function. Non-vanishing holomorphic function. And if you have the like the motivation to look at the definition of the like the exactness for the shifts, then the important like the example should be the log. Log is very important, like the example. So, but let me just skip to talk about the details. So once we have the short exact sequence of these shifts, then this induces the long exact sequence. So that induces, say, so let me just start from H0. So MZ, H0, MO, H0, MO star, and it just connects. There's a connecting like a map that maps like this. Let me just write down in the stage of the H2. So this is guaranteed in the level of the ships. So it goes forever, basically. So in this description, as you can see, there's no consideration of the neither Kähler metric defined on the complex manifold, nor there's no Hermitian metric on the line bundle. So there's no such a consideration here. However, so at least I hope you can convince yourself we have this map. We have this map, and we can just assume this is the abelian group. So these are the abelian groups, so that this like the map is the group homomorphism between two abelian groups. This is actually exactly C1. C1, so what we usually actually do is so for each like yeah, let me know if you have any comment. So that the each like the element here is just nothing but the equivalent class of the line bundles. So for each like the line bundle, so there's a abstraction that so this is called the so-called the Picard group, or the Picard group, so that it maps to C1 of the L that actually only depends on L, only depends on L. So and you can identify this guy as just a Z, this guy as a Z, so that we can talk about whether or not this is positive. Whether or not this is positive. This means the following. So that so let's just put just one Hermitian metric arbitrarily Hermitian metric. So sorry for my very like the sketch like the note. So about this is just for the triggering the conversation. And if any of you want a clarification further, then I'm very happy to provide such a like a note later on. So then just choose holomorphic sections. I mean non-vanishing sections. Say just S. Then this H of S becomes positive, so that we just put the log and put dd bar, this guy. So this becomes differential two form. Then what we can do is we can simply just take the integral. So let's just assume this has just a desired like the dimension, but there's a way to just adjust. Then this actually value becomes the integer. This is actually the Gauss-Bonnet theorem. So that's why we can talk about, so, and this quantity is called the C1 of L. So there are two different like the ways to describe, but this is just a very rough in a sense that, so I just assume this is dimension, complex dimension, just for a moment, just a one, so that it makes sense to talk about the, just take the differential two form for the integral. So this is just nothing but rewriting the Gauss-Bonnet theorem. So there's two ways to go around. So number one, for the definition of the C1, so in the level of the long exact sequence, it does not require any differential geometric data. So that we can always talk about just this like the abelian group homomorphism. And because if we just identify this guy as just a Z, they are actually like the isomorphic as abelian groups, just a Z module, then we can talk about the sign, but in differential geometric data, so that we just make the curvature two form from the chern connection, and then we take the integral, then Gauss-Bonnet theorem says that up to 2 pi, it becomes the integer. So that we can talk about the indeed the sign of it. So now let me just go back to the statement. I know this is very rough. So yeah, so if there's a further necessary like a clarification, let me know. So that's why we can say first chunk class is being positive. So you can just assume that. So we have a collection of the line bundles. That's the H1 of the MO star, or this is called as a Picard group. Then we can talk about the sign. And you can also say that this sign just means the total value of the integration, basically, if and only if this condition is algebraic geometric condition, ampleness. This is also completely like, independent to the condition of neither the Hermitian metric nor the Kähler metric. But when we describe this, when we have the Hermitian like the metric, then we just have the description of this in differential geometry, just that's all. So what I meant, just again, I never said that we are able to construct the interesting Hermitian metric on the line bundle in general. So let me just go back to the statement. I never ever said that we are able to construct this guy nicely for the general like the general line bundle. However, if we just assume that we have a like the Hermitian metric on the line bundle with the section, then we get this. Then we have the description C1 nicely. And Calabi conjecture already assume we can do so. So such a construction and existence actually matters. But so you can just assume just assume that if we can construct a Hermitian metric with the if you have a dissections, then we can do so. But the condition here is nothing to do with the differential geometry condition at all. That's one thing. And so let's just look at why this condition matters. What's the definition, so the meaning of this ampleness and why this condition really matters. So of course, the definition of ampleness is indeed just an algebraic geometric condition. So this means the following. So let's just look at this guy. So we have start from the holomorphic line bundle, and we have the at least local section. This is actually already tricky. So there's a way to describe without using any differential geometric data eventually in algebraic geometry, but let's just assume we have a sections. What does that mean? Section means we have a graph so that we have so these are just a holomorphic function defined on open subset U. And the codomain, we can just assume this is C1. Is that okay with you? By the definition, rigorous definition of section, these are not functions, but via the local trivialization, we assume sections are the holomorphic functions, C1 valued. So that's why it makes sense to just make the projective space, assuming the values are the complex valued. Again, these are rigorously speaking these sections. We cannot assume the values are actually C valued. However, via the local trivialization, we can do so. So that's why the domain here must be the open subset. So this like the setting depends on the local trivialization for sure. We need to worry about like this guy, but actually it's actually okay eventually. Then what's the condition we are wondering? So the condition we wonder is very like the ambitious like the goal. We will say line bundle is very ample in the case that we can extend this U to the entire complex manifold first, and this map becomes the embedding, holomorphic embedding. This is very ambitious like the goal. Such a case, we call such a line bundle the very ample line bundle. That's the definition. Is that okay with you? So that we are able to embed the given complex manifold in the some complex projective space. Is that okay with you? That's the concept. So in such a like the case, we call such a line bundle the very ample line bundle. And if that's not guaranteed, that because the line bundle is already given, so if you take the R times tensor, still the rank must be equal to one. We start from the rank one, like the vector bundle. Even we choose the tensor products, still rank should be one. So that we will say the line bundle is ample that if the tensor power of the some tensor power gives the concept of very ampleness. That's the definition of the ample line bundle. Is that okay with you? So now let's just look at this theorem. So you can just naively just interpret this as a very ample, because up to taking the tensor product, there's a very philosophical deep meaning of the taking the tensor product for sure. But let's just assume for simplicity that very ampleness just means what? So we can embed M as a closed sum manifold in the projective space. Such a like the manifold is called a projective manifold if and only if C1 of L is positive. So that means that the given complex manifold is in fact a projective manifold, meaning that the closed sum manifold of the projective space. Why this condition is important? Because this condition is important from the Chow theorem. So according to the Chow theorem, if complex manifold M is embedded into Pn, so let me say Pk, then M is an algebraic variety. This means for any point, we can find a neighborhood such that this U, this is nearby this U, should be written as a zero set of homogeneous polynomials. So that's why it is so important in complex geometry that for general Riemannian manifold, or we can expect this, we can embed that into the Euclidean space so that we can do something from the structure of the Euclidean space. So that's all we can say from the Witten's embedding, Nash embedding. So, and we can do some differential geometric data. Whereas if we have the so-called projective manifold, meaning that we have a holomorphic embedding from the complex manifold to the sum of the projectives at some dimension, then we can write down complex manifold M as a zero set of the finitely many polynomials. Then we can use the data of the ideas of the polynomial ring. So the geometric data can be completely just transferred to the purely algebraic data. So in order to do so, we should embed to the not Cn, but Cpn. And that is guaranteed from just finding the very ample line bundle, very ample line bundle. And the very ampleness is in fact coming from the first chunk class. So we know the characterization that as long as the first chunk class is being positive, then we know it becomes projective space. So that's why Fano manifold is very important in a sense that if we now choose this L to be the canonical line bundle. So now let's just go back to a various now question. So first, do we know that whether or not we can construct an interesting Hermitian metric on the given arbitrarily formed line bundle? The answer is I don't know. I don't think so. So we do not know such a construction can be done. So there is just a way to construct a smooth Hermitian metric, like a metric for sure, but the holomorphic, the Hermitian metrics, I'm not really sure. But so if we choose this L to be the canonical line bundle, then what's the benefit? Then we know that for the canonical line bundle, we can simply just choose Hermitian metric as a 1 over determinant of G. And this G, there are many choices, right? Because complex manifold is given, we can equate the Hermitian, like the metric in the level of the base manifold. Then we can just declare 1 over determinant of G is the Hermitian metric. And we know that our concept we are now talking about does not depend on the differential geometric data. So that's why it's just handy to just look at the canonical line bundle. That's one reason. But it does not mean that we should restrict our attention to the canonical line bundle. However, still we can link the word of differential geometry from the canonical line bundle. That's the key reason. So in that perspective, if you really look at what we said, so I am thinking the following. So the practical reason to just look at these three classes is that, so in this case, we can use both differential geometry and algebraic geometry. So if we just look at the general line bundle, general holomorphic line bundle, then we just lose this. Or we have just a curvature two form. So in that case, we just do not know that well compared to the current line bundle case. We do not know how to handle. But of course, there are the extensions of the work for the general line bundle. So that's my just a like the explanation. And so the you can see some interest like a consequence from here. So the definition of the funnel. So even I said this way, what is this condition? We just put canonical line bundle here, canonical line bundle, and this least positive condition just means the C1 of the canonical line bundle being positive. Is that okay with you? That's the meaning. Then if you just look at the consequence from the Godairas embedding theorem, we already have canonical line bundle, the first chunk classes being positive, then it must be ample. It must be ample. That means that we can find one very ample line bundle. That means that M should be embedded into where? Embed to the projective space. So therefore, funnel manifold is always algebraic variety. It should be written as a zero set of the polynomials. That's the one very important consequence of the funnel variety or funnel manifold. For the Calabi, now it is zero. This condition is now zero. So no guarantee to be algebraic variety. So indeed, Calabi-Yau manifold is in general not algebraic variety. So for complex dimension one, every compact Riemann surface are algebraic variety. No exception. So complex dimension one case, any compact Riemann surface are algebraic variety. But complex dimension two, so the Calabi-Yau is usually called by the K3 surface. So there are 20-dimensional K3 surfaces in the theory of the moduli space. So 19 dimension are algebraic variety. There's one dimension, these are not algebraic variety. So Calabi-Yau, that is first chunk class being zero, is in general not algebraic variety. And the negative curvature word of the negative least curvature word in general, these are not positive, it's actually negative. So that we cannot say about the ampleness in general. So the only guarantee like the class for that being algebraic variety is just a class of the funnel. And the reason why Calabi's conjecture is so important in algebraic geometry, algebraic geometry and complex geometry is the following reason. So in the context of the just a planar domain in C1 or a bounded domain in Cn, we are interested in the invariant metrics, including Kobayashi, Carthiodori, Kähler-Einstein, and Bergman. So that's the class of basically the class with the negative least curvature being sort of the negative. It does not need to be strictly negative, but that's the type class we are looking for. So the reason why this class is so important is the following. So, but let me just give you the statement of this guy. So this is just consequence from the Yau theorem. So Calabi's conjecture. Yeah. Again, I just try to explain very in the sketchy way. And if you need any clarification, send me the email. I will be very happy to provide all of the details so that I can also study. So Calabi's conjecture is now the following. Calabi's conjecture. M omega, let me say not. So we have a compact Kähler manifold. This is given. This is given. So all you need to just apply the d-bar lemma. So if we have two like the forms omega and eta, real one-on form, then we are able to find smooth functions, real valued smooth functions, such that this is the dilemma. Is it okay with you? This is the dilemma. So what we know is the following. So then Lipschitz omega naught is real 114. Is that okay with you? So that's just from the construction of the H2 tensor that I covered last like the time. So conversely, so this is a question. So just choose arbitrarily real one-on-four. So this is just a remark that we already know. We Leach two form becomes real one-on form if the Kähler metric is already given. And we already assume we have a Kähler metric here. This is already given. So real one, let me say eta. Eta is a real one-on form. So the question is, can we find, and in fact, this is already solved by Yao. So we can actually find unique Kähler metric. Unique Kähler metric omega. I'm not saying omega naught, which is given in initial Kähler metric. I'm saying we can always, there exists unique Kähler metric such that it satisfies two conditions. Number one, they share the same cohomology class, i.e., by Dirichlet lemma, because we said this is compact, so omega naught should be written as omega plus I times dd bar of f for some f. So that we have the Kähler metric coming from the same drum cohomology class of the given initial Kähler metric. Is okay? This is the first condition. Second, what do you expect? Leach of the omega. I'm not saying cohomology class. I'm saying Leach differential two form itself equals what? Eta. Such a like the metric uniquely exists in the case of the compact Kähler. This is Calabi out here. So hopefully now you understand this like the statement, so that if we put arbitrarily real one-on form, we can realize this as a Leach form with unique Kähler metric, that this Kähler metric share the same drum cohomology class from the initial Kähler metric. And if we describe this condition, this just becomes Monge-Ampere equation in like a PD perspective. So in order to find such like the omega, then we should set up this equation, right? And this equation just becomes the Monge-Ampere equation. That's all. And it also satisfies certain conditions here. And the uniqueness is very easy. So if you just assume this is a very like the only level gradual like the exercise. If such a like the metric exists for two metrics, then just you can simply just show they must be the same. So the uniqueness is very easy exercise. Existence is very hard like the problem. So this is a field matter result. So that just a setting of the Monge-Ampere equation for this second part and just solving it. So there are two different ways to do so. So let me just mention that we can also look at the details if any of you are interested in. So Yao's method is so-called the elliptic or the continuity method based on the a priori estimate. And another method is a parabolic method. There are two methods in general. And many people call this method so-called the Kähler-Leach flow. So initiated by Cal. So the technical details definitely matters from geometric analysis. I'm very also happy to look at any details from the original paper if any of you are interested in it. And this detail will also should be interested in like expanding the research as well in the community of complex geometry. But that's one thing. And another thing I wanna say is now let me go back to the reference of the external metric reference. So this is now a bit like the matters. So let's just now assume we know we are able to solve the Calabi's conjecture by Yao's like the approach. Yao's approach was just by solving the elliptic complex Monge-Ampere equation, and the parabolic approach is just a sort of the extension, but elliptic approach completely solved the problem. So please do not get confused that we are always able to do so. So please make sure that this omega is a Kähler metric, meaning that this is one of the real one-on form. Is that okay with you? We already have a real one-on form here. If we have such a real one-on form, the rich real one-on form should be determined accordingly. And we do not have such a like the control to write down those two real one-on form by some ratio lambda. Lambda is universal constant. This is not guaranteed in general. So Calabi's conjecture does not guarantee to find such a lambda, because Calabi conjecture says that if we start from the arbitrarily real one-on form, we are able to find the Kähler metric. Whereas this just means that we need to find omega satisfying this condition directly. This does not imply from the Calabi's conjecture. Is that okay with you? So logically, it's different. So that our like one of the interests is find the Kähler metric satisfying this very strong assumption. But still, if you want to apply the Yau's like the approach, in the case of the lambda equals negative, so the magnitude of lambda is just a matter of the scaling, so that we can just assume either lambda is either positive 1 or negative 1 or 0.
Yes.
So it's just up to the scaling issue. So scaling is there's no like the stress. The only like the issue would be just those three classes. So by applying Yau's method, these are just a direct correlate to truth be told. So Yau's method directly apply to construct the Kähler-Einstein metric of the negative Lich curvature with the zero Lich curvature. And this is a case of the Calabi-Yau manifold. The issue is about the funnel. So this is the positive Lich curvature. Such a metric in general does not exist. This case is the only issue that we are not in general able to solve by just solving the Monge-Ampere equation by any like approaches. It turns out that there are no topological obstructions to solve the Kähler-Einstein metric of the non-positive Lich curvature, no obstruction. However, there is the obstruction to find the Kähler-Einstein metric in the case of the funnel. And it turns out, this is the purpose of this like the note, it turns out that the topological obstruction is the invariant in algebraic geometry. And this condition is called the K-stability test configuration. And let me just show you the statement. Bergman-Conner also naturally appears in this like the context. So where should I find? Let me try to find that one. Should be somewhere nearby here. Yeah, this conjecture is almost solved at this like the point, but still including like the Gantian. So people are still actively working on this conjecture. So many cases is already solved. So people want to know. So constant scalar curvature metric is one of the generalization of the Kähler-Einstein metric in the geometry analysis context. So people want to know whether or not we are able to solve the like the Kähler-Einstein metric existent in the case of the funnel. And we have a K-stability as a characterization. This condition is the algebraic geometric invariant condition. So let me just summarize in this way. So for our current like a conversation. So number one. So the classes are like the classified in terms of the Lich curvature. The reason is that the canonical line bundle is handy to handle, but it's not necessary. So we can still look at the general holomorphic line bundle and look at the general like the Hermitian metric, but in that case, it's just a harder. That's the only reason, in my opinion. There should be the like the problems that we can also work rather than the canonical line bundle case. But this is a general like the definition of the funnel, Calabi-Yau, and general type. Number two, for the funnel case, we in general do not know how to find. So we are asking whether or not there is a Kähler-Einstein metric, and such like the topological obstruction appear as a invariant in algebraic geometry like the objects. So that's called by the K-stability. And that's so very like the famous conjecture by Yao, Tian, and Donaldson. And so, some of the mathematicians in China are working this conjecture still very actively. And the case of the Calabi, Yao, and general type, there are no topological obstruction to solve the Monge-Ampere equation so that we can always find the Kähler-Einstein metric. So the contexts are now changed in a way that can we extend the smooth Kähler-Einstein metric, the singular Kähler-Einstein metric? That's one context. And can we establish some of the interesting consequences, such as whether or not we are able to establish the equivalence with the other invariant metrics, for example? Then, but this is not the case of the just a compact any longer. So that can we extend to solve the complex one-jumper equation with the different applications and so on. So the context is slightly not different. I know it's very like a rough explanation. And in either classes, the Bergman-Conner plays a crucial role in all classes, I'd like to say. So that so in the even class of the funnel, the Bergman-Conner plays a role, and Bergman-Conner actually plays a central role, in my opinion, for any class, including the bounded domain in CN. Yeah, so that's my today very sketchy and rough, bad explanation. Sorry for that. So yeah, so let's just finish our conversation in short after I like hear you listen your like the questions or like a remark or and like the request, and let me just go give you my answers back, and yeah, and
So,
including the style of today's like the conversation. Sorry for that.
I really like this format better than the one before. I think
Okay.
I think for the next session we can try two more things in addition. When you're sharing the like, recorded lecture notes, it will be nice if you can share some references where we can look into the details. For example, if you're defining something within the lecture and we have to see exact, precise definition of what this is and so on. It's better if we go back and look at it. So it's better
Yep,
if
yep,
there is
yep.
some reference just for that lecture alone. One. Two, it will be nice if we come with a set of questions to ask before we begin. So before we begin the session, we can come up with a set of questions so you know exactly where we are stuck at and what are the questions that we have in mind. So it will help you also answer much more. Okay, so these two things I feel will kind of sense here.
Yeah, absolutely. Yeah, thanks for the like the comments. Yep. So I think I should also initiate the conversation in email so that I can also receive other like the requests from the other participants as well. Yeah, thanks for the comment though.
And I personally find myself I need to work on becoming more comfortable with the uh, uh, you know, the algebraic structure in the sections, the like uh, uh, so all the notations. For example, many of the notations looks to me like playing with the notations, like uh, exactly what do they mean. For example, one of the questions that I thought of asking today is the smooth sections have a graded algebra like structure, right? So uh, uh, the point is like 2 points. First is like when you collect all sections, what is the algebraic structure on it? I'm sure it is it's a model overseen through the FM. Then what are the algebraic structure on it? One. Two, when we say there is a graded structure, what does each AK mean? For each K, we are just tensoring it, right? But when you mention seeing smooth sections, I can imagine that as like the diagram. I really like the diagram where you have the base manifold, and on each thing you draw the, for example, bundle fiber, and then it's just distorted over the bundle. So if it's smoothly distorted, it's just smooth section. Now, what does the tensor product mean in the sense like when you take A1, what does it mean? What does A2 mean? Geometrically, is there some understanding that we can build?
Yep.
Um, yeah, we have some answer for that before.
So let me try to naively explain in a sense that this will determine the direction of our further conversation in this like the seminar. That so if some like the directions are very highly motivating us, then we should just pursue that direction. So let me just very lively go over Alan's like the or like the comments now, and let me just go back to like Barry already leave for his like the situation. So let me just share the iPad. So so there are several things. So one. So if we have just the smooth vector bundle
Mm.
over smooth manifold. So one of such a, like the example should be either the tangent bundle, or
Yeah,
the cotangent bundle. Those are
line.
the canonical like
Mm.
the such a like the
Yeah.
examples. Then the
Mm.
section, um, so it depends on the choice of the open subset. So for this guy, so this is a collection of the vector fields on U, vector fields on U. And if we have this guy, this is the differential forms. Differential one form on U. So that these are the examples of the smooth sections. It should say smooth local sections in a sense that, so if we describe each like the vector fields, then we know we should write as a I, ddxi, and the corresponding function. And these data are smooth. That's the meaning of the smooth sections. And differential form, so say omega, should be also write as a dxi summation, and also should be written as a h sub I. And these are just smooth. That's the meaning of the smooth section for these examples. So that in general, so if we look at just a smooth vector bundle, then if so there's just a corresponding local sections, say local sections, then we are able to write this in terms of the linear combination of the bases, and there should be the corresponding like the coefficient functions, and we require this to be smooth. That's the meaning. So now if we require it to be so because you are asking about the algebraic section, I will go for it for that, but then we just move this to the holomorphic. That means that the local coefficient function should be holomorphic. That must be the meaning. Otherwise, doesn't make sense. So the tricky part is the following. So when we talk about it's not the rigorous term, but if we say at least the intuitive about the algebraic section, what does that mean? That means we already change the data in algebraic, like the purely algebraic data in the following way. So for example, so in Godira embedding, so what we used is that, so we start from the complex manifold, and then we have a holomorphic line bundle. And for concrete like the example, we can simply just choose L to be just Kn. So canonical line bundle if you need. So in such a case, section is behave like dz1 wedge to the dzn, and there's just a function here. And because we said it's a holomorphic line bundle, we just require this to be holomorphic. Just that's all. So this is a concrete shape of the holomorphic local section for this example. So hopefully this gives some like a good intuition. Then what Godard embedding did is that just choose sections, local sections. It actually should be this form in the case of the canonical line bundle. So choose local sections, say S1 to SK, then according to the rigorous definition of the section, then we should say, because we have a map from L to M. That's all we have. And this map itself is holomorphic because L is also another complex manifold. So that each like the section, all we have is just this is identity. This is just definition of the section, rigorously speaking. However, via the local trivialization, localized trivialization, then what we have is, so on, let me say U, so we can just assume each S of I are the function from U to C. This is already tricky in a sense that we already identify this guy as a U cross C, so that each like the point, we just, and section actually sit inside of here. Does that make sense to you? So that
Yes.
we already just take indeed the product structure locally, so that we kind of ignore U for the section, so that we indeed regard, in truth be told, we actually should say this. However, we just drop out this U by just saying, well, we have a local trivialization by the definition, so that we can do so. So that now we already regard the holomorphic like the section as a indeed holomorphic function in this like the context, holomorphic function, and then we just map each point to S sub 1p to S sub kp and create the projective space in this way. So this only makes sense via the local trivialization, which is not guaranteed for the general section without the local trivialization. So that, and the very ampleness looks weird because we said, so suppose we define this local map. This is only the local map, so that it doesn't make sense to expand this open subset to the entire manifold, because that means that we can do the local trivialization for the entire open subset. That's not allowed in general for sure. So the condition of the Godard embedding looks doesn't make sense in a sense that so if you look at the again definition. So up to here, yeah, we can agree. So because we have a local trivialization, we can do so. But if you look at the definition, in fact, such a map defines the embedding. How can that make sense? Because we cannot to take this M to be the local trivial. That means the line bundle should be already the trivial line bundle, just an M cross C. Doesn't make sense because line bundle should be not trivial. So how this definition makes sense? There's an actual way to go around. So this is now the part I should explain. So not the the mathematical rigorousness, but truth be told, there is a way to transfer the data. So line bundle. This line bundle can be changed as a data of the so-called Gardier divisor. This is one-to-one correspondence. So in fact, this is tricky differential geometric data. This is really tricky. This is mathematically correct, but this is tricky. First be told, the map is defined in this way. So M, data map, this guy is not this one. This is in fact coming from the following. And this can be also, so there's also one-to-one correspondence, so-called the invertible shift. Because we were talking about the concept of the shift over here. Where was it? We were talking about the concept of the shift on the in terms of the short extents, like the sequences. Then what this actually is, if I just denote also this by D, then this is H0 of D, and this is C K plus 1 as a C vector space. And take the projectivization. So that this data does not require local trivialization. And this data is purely algebraic. So this data is differential geometric way to represent projectivization of the zeros cohomology corresponding to the invertible shift from this line bundle. That's the rigorous this description. So that the algebraic section is actually sit inside of here as a element of the projectivization of the H0. That's one thing. And about the second point is about the intuition about all those cohomological data. What is the meaning of the H1 of O star? As I said, it's a Picard group. And what's the meaning of the identification of this guy correspond to Z? And how do we really identify this guy as just a C1 of the case of M? So that this is indeed coming from the differential two form, something like this. So this is about the interpretation of Gauss-Bonnet. So and if any the mathematician who need to study the complex algebraic geometry, then in fact the identification of the line bundle, Gardier divisor, invertible shift are required, in my opinion. This is essential. And this a cohomological data is should be interpreted with the what? Compact Riemann surfaces and Riemann-Roch theorem. And these are the key to open the door to understand all those the abstract cohomological data to just represent either the differential geometric data or the purely algebraic data and link those two separate words very broadly. So yeah, this is also another topic that I can also go over in this seminar, but it takes time. So because this is also a big topic. So if I open this like the Riemann-Roch theorem or complete Riemann surface for the like the graduate level class, it should be the one semester actually subject. But I can try to shorten. So if any particular including you are interested, that's my answer.
So basically, now I just want to share how it is. So I feel a bit overwhelmed because of especially because I'm not able to follow a lot of notations and what's happening. For example, you might say somewhere that this is a true form and probably this is a real one
Yeah.
form and then move forward. But for me, like since I'm looking at it for the first time, I have to actually sit and verify why this is a true form. Like why does it make sense? Like we're just writing in a faster way. That's exactly happening because I'm looking at it for the first time. And second, I don't have examples or exercises or some standard reference of a basic material that I can go through before our session, so that in our session I'm more comfortable with all the notation basis. So with that in mind, let's be honest, like, is there some material that you would like to go through in parallel? Just for the basics, all the basics that are research or whatever we are discussing. Some material, some chapters, some sections that you want me to go through.
Yeah, you actually make a very valid point. In my opinion, so if people study differential geometry, there are the well-known like the references. If people study algebraic geometry, people usually study like the Hartshorne and so on. In studying complex geometry, so
Mm.
I should say that it doesn't mean that I recommend to do so, but what I did in my first year of the PhD was uh, by studying the reference of Griffiths-Harris of the principles to algebraic geometry, but it consumes the period indeed a lot, and this will not just jump people to initiate the research, in my opinion. So
Mm.
my personal recommendation of the following. So I think the important like the example to look at for like the digesting all those like the highly abstract like concept, one should look at the torus, just the elliptic curve, torus. And I'm very happy to look at the torus together to just start from the just a so torus just means that just a R2 quotient out by just a Z2, right? Homeomorphic to just
Mm.
that
Mm.
guy.
Mm.
And this is compact like a Riemann surface. So this actually gives all necessary like the theory. So today let me just share one reference for you. So this is
Mm.
in my opinion, very enough to understand all like the machineries eventually, so-called the Jacobian of the Riemann surface. So let me just share that reference here. And it doesn't mean that I know you're very busy, so you do not need to study this. I can happily explain this in this like the seminar upon the just a request for sure. So you can simply just search Jacobian of Riemann surface. For one clarification, Jacobian does not mean the Jacobian matrix and a multivariable like a calculus. It's completely different meaning. So Jacobian means completely different. So one just need to understand. This looks very weird. So if you just take, so if you just look at it here. So I think just understanding this short like the article is very enough to understand all those like the abstract like languages, in my opinion.
Mm. Mm. Mm.
Yeah. So, but yeah, I'm very sorry that I actually really want to say this is a best like reference in complex geometry, so that the beginners should study that. But in my opinion, there's no such a like a reference. So maybe a senior like the mathematician should do so. There are some references for sure, but in my opinion, there's no best reference. So that depending on the like context, one need to like look at the different like the references, and one need to look at still the complex like the torus, complex torus, and the Jacobian is about the torus. So, and once one understands it, one can understand all my language today I talk about in terms of the concrete like the torus in this context.
And let me try to go through the article, and probably next time when I come, I'll ask one or two questions
Yep,
so that
yep,
we can slowly like build the understanding
absolutely,
of our
absolutely.
thoughts.
Yeah, I'm very happy to do so. And let me stop the record here.